All right, so we want to talk about what calculus is today. And we're going to use a single example to illustrate the two key concepts of calculus. So let's imagine that we're taking a trip to my grandmother's, who lives down in Maryland, and she's about 180 miles away. Now, it turns out that you can get there by interstate. So if I leave really early in the morning, let's say 4 a.m., I can just set the car to cruise control at 60 miles an hour, and 3 hours later, I'll end up 180 miles from my house and at my grandmother's house. So we represent that graphically by the fact that when I leave, the time is 0 hours, and the distance I've gone from my house is 0 miles. When I finish, I've gone 3 hours, and the distance away from my house is 180 miles. Now, because I had the car constantly at 60 miles an hour on cruise control, we can also determine where I was at any point in time along the trip, and that's what this line represents. Now there's something else that we can do, and it may seem trivial at first, but you'll see that it has greater significance later on, and that is we can calculate the slope of this function. The way you calculate the slope of a line, as you well know, is to take the change in y divided by the change in x, and that gives you a numerical value. In this case, 180 over 3, which is 60. And the units, in fact, are 60 miles divided by 3 hours. And so this slope actually represents something more than just a slope. Namely, the slope here represents the speed that I was driving at, 60 miles per hour. The problem, of course, is that nobody really drives this way because there's traffic. So let's look at a slightly more realistic case. In this case, after an hour, I'd made it 30 miles, let's say because I got off to a late start and there was a lot of traffic. Then the traffic cleared up, and so from the first hour to the second hour, I was able to drive an additional 60 miles. However, I noticed that I was getting late because I'd hoped to be there at a certain time, and so for the last hour, I drove 90 miles. Now we can also ask the question of this function. What is its slope? But it's sort of a nonsensical question because this function doesn't have just one slope like in the previous example, but in fact it has three separate slopes depending on when we're talking about. So if we were to choose the center section, we can still talk about the slope of that part of the function that's a straight line. So the slope from hour 1 to hour 2 is again the change in y over the change in x. 90 minus 30 over 2 minus 1 gives us 60 over 1. And again we see that the slope is the same thing as the speed, namely 60 miles per hour. However, as you all know, getting to Grandma's house is really something far more complicated than that in the real world. What really might happen is something more like this. We take off, things are going fine, and then we decide we want to have a pit stop, maybe at Wendy's, get something to eat. So from about a half an hour out until an hour, there's no progress made at all in distance. Then we have to hot foot it in order to make up for lost time. Now, along about this point, we realize that we're not even close to making it on time, and so we decide to take a shortcut. Unfortunately, this shortcut isn't really what we thought it was, and it actually ends up taking us backwards, closer to my house, rather than closer to my grandmother's house. So at about this point, we realize that we're in really deep trouble, and we go at a speed that I do not want to document because it's a little bit dangerous. But in the end, we end up at grandmother's house after 3 hours. Now, if it was odd to ask what the slope of the function was in the previous case, namely the case where we had three different slopes, It's even stranger to ask what the slope of this function is. And that's, of course, because this is just a continuously varying curve. Who's to say what the slope is? Except for the fact that you can talk about the slope at a particular point. Well, how do you do that? Well, slope is still change in y over change in x. It turns out that for suitable functions, and we'll spend a lot of time talking about what suitable means, you can actually blow up the function, a small piece of it. And if you blow it up big enough, that little piece of the function always looks like a straight line. Well, in that case, you can take the change in y over that little window, divide by the change in x over that little window, and you'll come up with something that is closer and closer, an exact approximation of the slope at an instantaneous point. We call that the instantaneous slope. And in fact, the first key concept of calculus is nothing more than the instantaneous slope at every point of a function. That has a special name. It's called the derivative. See if you can't teach your parents that.